Let's talk about induction. So, what is induction or mathematical induction? It's a proof technique. So, here's like a way in which you can think about it, right? So, let's say I have this infinite, like infinite row of dominoes. So, pretty much one domino is going to knock down the next domino, and that's going to knock down the next domino, and so on. So, eventually, every single domino will fall. Okay, so that's still kind of vague, right? Let's talk about it a little bit more in detail. Okay, so here's like the formal outline for mathematical induction. So let's say I want to show that some statement is true for every value of n, which is at least equal to k. Okay, so I want to show that it's true for every single value of n after k. So here are my steps. So first I got to show that it's true for k. And this is called the base case. Now I have to assume that it's true for some value of m, which is greater than or equal to k. This is called my inductive hypothesis. And based on this assumption, I have to show, okay, if it's true for m, it has to be true for m plus 1 as well. So that kind of shows that that like establishes the connection. Like if I have a domino, like that establishes the fact that one domino is going to knock down the next domino. Okay, so if you can basically show the base case, and based on the inductive hypothesis, if you can just show this inductive step that if it works for m, it works for m plus 1, then it has to be true for all values bigger than or equal to k. Okay, maybe you have some idea of how this works, but I'm assuming that most of you still don't. So let's go ahead and work through a few examples. Okay, so here's our first example. So some of you, I'm sure, know this statement, but it says that the sum of the numbers from 1 through n is equal to n times n plus 1 over 2. So there are other ways to prove this as well, but we can also prove it with induction. Okay, so our base case for n is equal to 1. We do notice that the formula works, right? If I do 1 times 1 plus 1 over 2, that does equal to 1. So the formula works. Okay, so now here's our inductive hypothesis. Inductive. I don't think it really matters what you call it. Oftentimes I don't even explicitly write like inductive hypothesis. I just write assume this, so this. And I think that's actually what I'll be doing in this lecture. Okay, so assume that the formula works for 1 through m, right? So the sum from 1 through m is equal to m times m plus 1 over 2. Okay, so our goal is to show that the formula works for m plus 1. What does that mean? Our goal is to show this, right? When I replace m with m plus 1, I just get this. M plus 1, if I just replace that m with m plus 1, I'll get m plus 2. So I just want to show this, right? So let's go ahead and start by writing out this expression, 1 plus 2 all the way to m plus 1. Notice that this is equal to this because I have assumed that in my inductive hypothesis. Now I'm just adding on an m plus 1 to it. Okay, so I can like merge these into a single fraction. So I have m times m plus 1 plus 2 times m plus 1 over 2. And then I kind of just use a distributive property to go from here to here. So it's equal to this, which does actually equal to what's expected from our formula. So we're done. So we've proved that the sum of the first n natural numbers is equal to this. And if you do want to write that at the end, you can just do it like this. If you want, you can, so we are done. Okay, so yeah, so this is cool. All right, let's go ahead and try to work through some examples ourselves. So prove that the sum of the sum of even numbers is equal to n times n plus 1 for all n greater than or equal to 1. Okay, so let's go ahead and look at our base case. And actually, we can use more than one base case. You don't really need to most of the time, but let's go ahead and use more than one base case so we get some intuition. So first of all, like 2, how do I write that as 2 times something? Notice that 2 is 2 times 1. So 2 should be equal to 1 times 1 plus 1. Is that true? Well, yeah, it's true because 1 times 2 is 2. So that's good. Okay, let's do it like this. 2 plus 4. 4, you can notice that it's 2 times 2. So this should be equal to 2 times 2 plus 1. Well, is that true? Well, 2 plus 4 is 6. 2 times 2 plus 1 is 2 times 3, which is 6. So this is also true. So our base cases are good. Okay, so now let's go to our inductive hypothesis. Okay, and I'm actually writing this out. You don't have to write out this word itself. I usually don't. Okay, so let's assume that it works until, I like to call it k personally. So I'll just say assume it works until k. Assume it works for k. Okay, so based on this, I want to show that it works for k plus 1. And then if I can do that, like basically we've proven this entire statement. Okay, so let's go ahead and do that. So 2 plus 4 plus all the way until k, until 2k plus 2 times k plus 1. Okay, so this is equal to k, so like this part right here, right? We've assumed that it's equal to k times k plus 1. Okay, and then I'm adding 2 times k plus 1. Okay, and now I can use the distributive property. This is just equal to k plus 1 times k plus 2. And notice that this is what we expect based on the formula for k plus 1. Why is that the case? I'll just use some parentheses to just show you why. This is equal to k plus 1 times k plus 1 plus 1. Okay, yeah, so we notice that this is what's expected from the formula. Okay, so I'll just write, so we are done. You don't have to write it like this. If you want, you can actually write the exact statement. You can say like, so 2 plus 4 plus all the way till 2n is equal to n times n plus 1 for all n greater than or equal to 1. I would say if you're being really precise, you should write that, but I personally don't care about such excessive formalism. Okay. So now let's go ahead and prove this statement. So the sum of the first n squares is apparently equal to this. Okay, so let's just try out a base case. Okay, so 1 squared, is that equal to 1 times this? Okay, so this is 1, this is 2, this is 3. I'm multiplying them together. 1 times 2 times 3 over 6, that's 1. 1 squared is 1, so this is good. Okay, so now I'm going to assume that it works for k. This should be a K, by the way, not an N. Okay, so now I want to show that the formula works for K plus 1. So the first question here is, what should the formula even look like for K plus 1? Like I should know, like, I mean, I could like just write out the solution for you and show, okay, that this is like the right form, but like, that doesn't really show you the intuition of how I'm doing what I'm doing. Like I should show you what I'm looking for. So if I plug in K plus 1 into the formula, I'll just write it up here. I will get K plus 1 times K plus 1 is K plus 2 times 2 times K plus 1 plus 1. You'll figure out that that is 2K plus 3, and all of this divided by 6. Okay, so I'm basically looking for this formula. Okay, so I'm just going to keep that in my mind and I'm going to kind of hunt for it. Okay, so I've assumed this. Now I want to show the following, or I'll just write it out like this. So 1 squared plus 2 squared plus all the way until K squared plus K plus 1 squared. I want to rewrite that somehow. Okay, so I'll just start out with this formula, like what I have here. So I have K times K plus 1 times 2K plus 1 over 6 plus K plus 1 squared. Okay. Okay, so I noticed that I have like a K plus 1 here and I have something here. So maybe I should factor out a K plus 1, but before I do that, I should combine the fractions. So maybe I'll skip a few steps, but K plus 1, and when I do K times 2K plus 1, I will get 2K squared plus K. Okay, so now when I just bring this, like when I make it over 6, I'll get K plus 1 times 6K plus 6. Okay, so now I can combine these, like I can use the distributive property. I have K plus 1 times 2K squared plus 7K plus 6 over 6. Okay, and this form is not exactly like this final form, but I think we're close. Like this K plus 1 matches, the 6 matches, these don't match. So I think I can just factor it at this point, which I can. Okay, so this is equal to K plus 1 times, I think, K plus 2 times 2K plus 3 over 6. So in particular, when I do K plus 2 times 2K plus 3, I will get 2K squared plus 7K plus 6. Okay, so it matches with the expectation from my formula. So at this point, I'm done. Okay, so I'll just write. So I'll just say, so the statement is true. Statement, claim, whatever. Okay. Now let's go ahead. Let's see. Yeah, I guess we've already done this. Okay, let's talk about strong induction now. So strong induction is pretty much like mathematical induction, but it's stronger. So what do I mean by that? So in mathematical induction, we have our base case and we assume that a statement works for a particular value K. Okay, so with induction, like regular induction, we assume it works for a particular value K. For strong induction, what we do is, okay, we're not only assuming that it works for a particular value k, but we're assuming that the statement works for k and everything below it as well. Okay, so it's like a stronger assumption, but it's still something which we can assume. And a lot of the times, like when I'm trying to do a proof by induction, I'll, in my head, know that I can use strong induction whenever I see fit. It's not that I always need to use it, but it's something which is very obvious for me to use. All right, so let's go ahead and see an example. So in this example right here, we want to prove that any integer greater than 1, we can write it as the product of prime numbers. Okay, first of all, what is a prime number? That's a good place to start. So a prime number is two things. It's a positive integer, and it only has two factors. Okay, so another way to think about it is it's just divisible by 1 in itself, and it's not 1. All right, so let's just look at our base case. If we want to do more than one base case, that's totally fine. I'm just going to do one. So 2 itself is a prime. So like we're good with the base case. All right, so now let's use our inductive hypothesis. So I'll just say assume that the numbers from 2 to k can be written as the product of primes. Okay, and if you want to write it, you can say strong inductive hypothesis. Okay, so I'm assuming this. I want to show that k plus 1 can be written as the product of primes as well. Okay, so let's go ahead and look at k plus 1. So k plus 1, first of all, it actually could be a prime number. Okay, in this case, the statement is obviously true, right? It's a prime number, so it is the product of primes. And if it's not a prime number, it is a composite number. And in this case, I can say that k plus 1 is equal to a times b, where a and b are integers, and these integers are between 2 and k. Okay, so I also have this. So I'll just say a and b are integers, and then 2 is less than or equal to this, right? Okay, so I noticed that a, since it's between 2 and k, a is the product of primes. And b, since it's between 2 and k, b is also the product of primes. So I'm taking a times b. I'm taking a product of primes times a product of primes. So that means, like, I can just write this, that k plus 1 is equal to a times b, which is equal to, this is not like very formal notation, but I'll just say product of primes times product of primes. And like, that's just the product of primes. So since k plus 1 can be written as a product of primes, we are done with the proof. So the claim is correct. All right, let's go ahead and do one last problem. We will need to use strong induction for this one. Okay, prove that every amount of postage greater than or equal to 12 cents can be made using only 4 cents and 5 cent stamps. All right, so let's go ahead and look at our base cases. I do want to use more than one base case just so it makes the proof easier to write. I might not be using the fewest number of base cases, but that doesn't matter. We'll still solve the problem. All right, so let's say I'm trying to make 12 cents. I can make it like this. Let's say I'm trying to make 13 cents. I can make it like this. Let's say I'm trying to make 14 cents. I can make it like this. Okay, and I could write more, but I think this should basically give the idea. So, I mean, I clearly know that everything from 12 to 17 works. Okay, so now I just have to prove that it works for like assume it works for some number for like all numbers k, where k is something bigger than 17, and I just have to show that I can make change somehow. That's like the intuition. Let me just write down specifically what I mean. Okay, so assume I can make change for all numbers from 12 through k. And then I'll also put in the caveat that k is greater than 17, because 17 is a base case. I don't really need to, like, I know everything between there works. Okay, assume I can make change for all numbers from 12 through k. I want to show that based on this information, I can make change for k plus 1 as well. Okay, so here's like an idea, right? Like, if I can make change for all numbers from 12 through k, I want to make change for k plus 1. The most natural way for me to do this is, okay, k plus 1, right? What happens if I subtract 4 cents from it? Then I have k minus 3, and I can already make change for that because I've said that I can make change for it. So notice that k plus 1 is equal to k minus 3 plus 4. Okay, so in order to make the change for k plus 1, I can just take the way to make change for k minus 3, and include an extra 4-cent coin. Okay, so therefore I can make change. Okay, so why did we need to use strong induction here? Because I use the fact that I can make change for k minus 3 cents, right? And before with induction, I assume that I can, like, if I were to just use regular induction, I would assume I can make change for k cents, but that wouldn't really tell me that I could make change for k minus 3 cents. So that's why we're just using a stronger form here, and that just lets us solve this problem.